Here's an example where we're asked to find a basis for, sorry about the background noise. We're asked to find a basis for a subspace of R3, in this case, where every element of the subspace has to have this form. First entry is A minus B, second entry is A plus B, third entry is 2A plus B, where A and B are some real numbers. So we want to find a basis for the orthogonal complement. So the collection of all vectors that are orthogonal to every vector in this subspace here. So just taking maybe a straightforward approach, what we're looking for then is the collection of all vectors, let's say x1, x2, x3, such that the dot product of this vector x, x1, x2, x3, with some random vector in this subspace W, so the entries we know have to have this form A minus B, A plus B, 2A plus B. This vector x must be orthogonal to just any element of W, and so this dot product needs to equal 0. Okay, so then the way we calculate the dot product is first entry here times first entry here, so x1 times A minus B, plus the product of the second entries, so x2 times A plus B, plus the product of the third entries, run myself out of room again, but x3 times 2A plus B. 2A plus B. And I'm going to put the equal 0 over on this side. So that dot product should equal 0. Okay, so I'm going to multiply this out. So this part's going to be a bit dull. But so 0 equals A times x1 minus B times x1 plus A times x2 plus B times x2, and then 2A times x3 plus B times x3. So we want this to equal 0 for any values of A and B, because A and B can be any real number. And we want this vector x to be orthogonal to every single vector we can come up with in this form. So suppose I collect the A terms. So A. So I'm going to write this as 0 equals A times x1 plus x2 plus 2 times x3. Okay, that's with the A terms. And then the B terms, if I combine those, so I have here, here, and here. So if I factor out B from those terms, so plus B times negative x1, positive x2, and positive x3. Okay, and again, I want this sum here to equal 0 for any value of A and B. A and B can be any real number, so we certainly can't insist that either of those values be equal to 0. So if this sum is going to equal 0 for any value of A and any value of B, then we need this part right here to equal 0, and we need this part right here to equal 0. So that's going to give us a system of two equations. First equation will be x1 plus x2 plus 2 times x3 equals 0. Second equation will be I'm going to use red. But the negative x1 plus x2 plus x3 equals 0. Let me jot that down. Negative x1 plus x2 plus x3 equals 0. Okay, and you could solve that system either by substitution or with a matrix. I think I'm going to use a matrix to solve it in just a minute. Let me point out one other thing while we're looking at this. No, actually, here, let's just solve it. Sorry, I'm changing my mind again. So we want to solve this system. I'm going to use a matrix. I suppose, no, I'm going to keep that there. Get rid of this. Okay, so if I make my row 1, 1, 1, 2, 0. Second row, negative 1, 1, 1, 0. Okay, this is a straightforward one to row reduce. So if I do row 1 plus row 2, 1, 1, 2, 0. 0, 2, 3, 0. Okay, if I do, let's say I want to make this entry a 1 now, so 1/2 times row 2. So it's 1, 1, 2, 0. I think I can fit it here. 0, 1. I'm multiplying by 1/2, so this will be 3/2 and then 0. Okay, and then just one more row operation. I'd really like to keep this equation here because I wanted to come back to it in a minute. So I'm going to squeeze this last row operation right here. Sorry about that. But if I do negative row 2 plus row 1, I'll have this thing in the RREF form. So 0 plus 1, so that's still 1. Negative 1 plus 1, so this is 0. Negative 3 over 2 plus 2. So remember, this is negative 1/2 plus 2, so I'll be left with positive 1/2, and then 0 plus 0. And then I'm leaving this row alone. Okay, so solution set. I'm going to erase and write up here. I know this thing's taking up a lot of room, but I want to say something about that equation in a minute. Okay, so I'm going to get rid of the row operations. Okay, so writing out the solution set. x1 plus 1/2 x3 equals 0. So x1 equals 1/2 x3. x2 plus 3/2 x3, right, equals 0. So x2 equals negative 3/2 x3. And x3 is our free variable. So if x3 is our free variable, that's where we can set up our parameter. So you could just let x3 equal t. And then, so our vector x1, x2, x3 will be 1/2 t. That should be negative, right? Sorry about that. Negative 1/2 t, negative 3/2 t, and then t. That would work. Or sometimes we do these little things like let x3 equal 2t. And if I use a multiple of 2, the advantage there is, okay, well then I can cancel. And so I'll have nice, clean integers as my entries in my basis vector. And so it's fine either way. I'm going to use this, though. So if I set it up that way, then my vector x1, x2, x3, so my vector x would equal, let's see, this would be, I'll write it out, negative 1/2 times x3, which we're letting equal 2t, and then negative 3/2 times x3, which again, that's 2t, and then x3 equals 2t. And if I factor t out of that, oops, then that means any vector x, which is in the orthogonal complement here, will be equal to t times negative 1/2 times 2, so that's just negative 1, negative 3, 2. Okay, so a basis vector for W perp here, sometimes what we call it, a basis vector would be negative 1, negative 3, 2. Now, if we didn't do the clever 2t thing here, if we had just let it equal 2, or sorry, x3 equal t, then our basis vector would be negative 1/2, negative 3/2, 1, which is also fine. Notice that that's just a constant multiple of this vector here. And if this is our basis vector, we're saying that all multiples of this vector are in this vector space here, the orthogonal complement. So any other multiple of this vector would also be a legitimate basis vector for that space. Okay, but so here's the answer that I would give to this question. Now, I was going to tie this back. There's a theorem that I mentioned previously in the notes that gives you a different way to look at this, where it's said that if we get express W as the span of two vectors, so this set W could be written, notice that we could break this up as A times the vector 1, 1, 2 plus B times the vector negative 1, 1, 1, right? So another way to express W This is where A and B are any real numbers. So this is the collection of all linear combinations of these two vectors. So W is equal to the span of 1, 1, 2, negative 1, 1, 1. Right? So if we've got spanning vectors for the space, then another way to find a basis, or to find a vector that's in the orthogonal complement there, is to find a vector x that's orthogonal to both of these spanning vectors. So we would say, okay, that means I want the vector x, so x1, x2, x3, dot product with that first spanning vector, so 1, 1, 2. I want that to equal 0. Well, notice that this right here will result in this equation. x1 times 1 plus x2 times 1 plus x3 times 2 equals 0. It would have given us this equation right here. And then we would do the same thing with this second vector. So take your generic vector x, which is in the orthogonal complement, dot product with that second spanning vector, set it equal to 0. That's going to give you this equation, negative x1 plus x2 plus x3 equals 0. So another way to get to this equation, and it probably is a little quicker, is to express W as the span of two vectors, and then take your generic vector x, dot product with each of those spanning vectors, set it equal to 0. And that would have been a slightly more efficient way to get to these two equations here. And then we would have done the same row operations, set up a matrix, do the row reduction to describe the solution set, and get this answer here.